So welcome everybody. I think we are getting started there. There are a couple of more folks joining around. So today we will continue from where we started last time. But yeah, I don't assume that you had attended last time for the introduction. So I'm going to give you a brief introduction to big data and then get started so that those folks who have missed out last time could actually catch up. Uh, So those who have actually attended this earlier, it might be a little repeat for them. But I think, yeah, in case you want to hang around, that's still fine. Others uh, can join later also, that's fine. But we'll get started today. The agenda of it is to finish the day one syllabus. And today, being the day one, we will look at big data. We'll look at Hadoop. We'll look at the fundamentals behind big data and the overall technology landscape, and then see the relevance of it from the industry perspective, and then summarize all of those what we learn. So today's session is going to be only 2 hours, I think so. It might get to 2.5 or depending upon how we go ahead. Subsequent sessions we are going to make it 3 hours. Since it is the initial sessions, it will take a little time to digest the concepts. So we'll go a little slower at the beginning, and the moment we finish 1 or 2 sessions, I think we'll be on full speed. So welcome again for all of those who are attending this for the first time. So here is what today's agenda we are going to do. We'll look at what is big data. We look at the overall technologies in big data, because big data is beyond Hadoop. So we look at all the technologies which are there in Hadoop, beyond Hadoop. Then we look at some of the traditional business intelligence problem and where Hadoop differs from there, some of which we would have covered last time. We look at the key characteristics of big data. Then we look at what is that a hype, what are the things which happens around. So we'll quickly go through this. This we have done it earlier, but we'll just quickly go through this for the folks who have not been there. And today's main agenda is going to be here. So we'll introduce to Hadoop. What is Hadoop? What is MapReduce? Terminologies, the current trends, what is the potential opportunities, and how long in the future where this technology is going to last. So those are certain things we'll look at. So let's get started. Today I'll try to keep it minimum of slides. This is how it's going to be every time. So not too many slides to begin with. Okay. So let's get started. So we look at introduction to big data, and that's our first topic of the day, looking at what is big data. And last time we did a small introduction to what is big data. So let me take that a little further. So we see that traditionally there are different types of applications which we have worked with. Some of the applications which we worked with were, let's say, enterprise applications. And enterprises applications actually are like the SAP, Oracle, and big middleware applications, the ERP applications, the CRM applications, and so on. So these applications were existing and they actually generated data. So some of these applications are not really packaged applications. They were also traditional homegrown applications which were there. So we had traditional applications, and these are where the .NET, Java kind of applications comes into play. So all these data, all these applications basically create data. So because data is the core of the any of the business. So they create data, and this data is stored in a traditional systems like an RDBMS. There are two ways where we stored the files earlier. We stored it in RDBMS or we stored it in files. Okay. So we stored it in RDBMS and we stored it in files. So this is where most of our data resides today in the enterprise. So similarly, if you look at from a traditional systems also, same story. They create data and they are also stored in RDBMS and files. Okay. Now this is where the next generation of applications started evolving, where people wanted to start building reports. They wanted to understand this data and make some decisions. So they built reports. So initially we scrambled for these reports. Then came reports engine. So reports started coming out from the reporting engine. So we got the likes of Tableau. We got the likes of Cognos, MicroStrategy and so on. So this reporting engine came into existence. Now when reporting engines came into existence, the challenge said that these reporting engines needs heavy duty data. So they needed data from all the places. So we built enterprise data warehouse. So this is how the journey started. So we built enterprise data warehouse, and the functionality of enterprise data warehouse was to make sure that it assemble all this data to a one place. So we bring the data to one place, and that was our intent. And from this we exported to using the reporting engine, created the reports. So this is a traditional life cycle of a data in an enterprise. So data gets generated in the transaction systems. It gets moved to the data warehouse environment, then to a data mart. Sometimes even from the data warehouse directly you take it and go to the reports. So this has been our traditional life cycle of data. Any questions till here? Understanding where enterprises has been till today. Any questions? Yeah, Ankit.
Yeah. I had a question. What's the difference between data warehouse and data mart?
Okay. So there is a small difference and sometimes there is a big difference. So data warehouse is a consolidation of all the data. Okay. So when we say data warehouse, it is basically a consolidated data store for the entire enterprise. Now what a data mart is, a small subsection of that from a business perspective. For example, let's say you take a large enterprise like Microsoft. So let's say Microsoft built a data warehouse for Microsoft entire company. So they will move all their data to data warehouse. But let's say there is a Windows product manager and he wants to analyze all the desktop applications. So he will create a data mart which only caters to a subsection of a data, but subsection of the data from different sources, all relating to desktop application. So you will create a subsection. So that is what is called as a data mart. So there would be multiple data marts coming out of a data warehouse. I hope that makes it clear. What is a data mart?
Sure. Thank you so much. Sure.
Okay. So folks, those are not coming from the data warehousing background. This might be a little terminology aspect. So I'm just trying to go through that terminologies and then we'll be all set so that next time we don't need to worry about all these terminologies. Okay. So now we have reached to understand what has been happening traditionally in an enterprise. Now let's go and understand what these reports are actually catering. When you look at these reports tries to understand what happened in your business. It tries to help you where it happened, and it also helps you understand when it happened. This is pretty much what traditional reports are supposed to cater to. They'll take the data from the databases, brings it down to the reports and reporting engine. For example, let's take an insurance company, and an insurance company is creating some BI reports today. So what they get the reports? They try to see how many new customers got in to me. So how many new customers came in? So this is one part of it. How many premium did I underwrite this time? How much is the new premium? How much did I pay for commissions? Then you will say, okay, which agents brought the most? Which geography brought it the most? And so on. And then say which time of the year that is my policies are selling more, and so on. So these are kind of reports which you try to get it and use these reports to make certain informed business decisions today. But the business has always been asking, why did my sales increase? Why did my sales increase 20%? Or why did my number of customers grow up 10%? And why did a certain geography the sales went down? So these kind of why question is not being answered. Why it is not answered? Because the data which we have been collecting is all the facts, all the things which actually happened. This doesn't answer why. Now, if you want to answer why certain things happen, you need to do something different. So let's say we want to understand why my sales increased 20%. So what is the easiest ways to find out that my sales increased 20%? First, you will go to the BI report and figure out which particular channel actually gave me an increase. For example, let's say after looking at that channel, you found that my online channels are increasing or my mobile channels are increasing. Let's say mobile channel increased by 10%. For that, now we need to understand why this mobile channel increased 10%. The immediate answer is this any of these traditional systems able to answer? No. We need to understand, is there any additional data which is available to help me understand it? And there is data within the enterprise. For example, customers has been calling the call centers. So there is customer interactions which are happening. So customer interactions are happening in the form of service calls, inquiry calls, websites they have been logging in. So there is website logs. There has been email conversation with our sales reps. There is campaign launched by our marketing team, and so on. So there are many other data which exist within the enterprise which nobody has been looking at because they are typically unstructured data. They are lying in some text files. They are lying in some log files. They are lying in some emails. They are dumped in some corner because it's too difficult to understand anything out of it. There is customer surveys. There is online social data which is existing. All that data exists, but nobody has been looking into this data. And this data is known as the dark data. Gartner has coined this word, dark data. So the idea is that this dark data is a data which exist in the enterprise but has never been analyzed or used. Now, how do you analyze or use this data? Because these are text files, these are emails, and this data can grow any day. And if you want to bring this into RDBMS, it is not going to work out because RDBMS cannot handle this data. So this is not working out. Even if you bring it, you can put it in a block file. So basically what you do is, you can keep only this file as files. Now when you keep this as files, when you want to process it, it becomes large compute power has to be there. Because you need large compute power to process it. Second part of the problem is, you need sophisticated tools to process it. You need to structure it properly. So these are certain things which are supposed to happen, and traditional systems are not able to do this. And this is where big data comes into play, where you need to be able to process this unstructured data and understand some insights from that data. The insights which you are going to get is, why did my sales increase? This is an example, but the answer to why lies into some of this dark data within the enterprise, and how can this dark data be brought to life is what one aspect of big data is trying to do. So big data is trying to address the dark data problem. Any questions till here? Any questions? Okay, so no questions. Okay, so let's move on. So this is one aspect of big data which we are talking about. That is from a business angle, why business is really looking at big data. Because there is a lot of dark data within the enterprise which will help me understand why certain things happened in my business. Now when you understand why certain things happened, the immediate question is, what will happen? So can I predict what will happen? So once you master the art of understanding why certain things happen, you will start and saying, can you predict what will happen? And this is where the analytics comes into play, where we are saying that we want to run large scale algorithms on top of this data and try to find patterns and trends on this data and try to predict based on the historical data what is going to happen in the future. And this is the area of big data analytics. Now analytics has been there all the time. It is not to say that people have not been doing analytics, but if you do today, traditional analytics are still on this structured data. So they are not able to get the real power of prediction. They can get some part of it. But when you start bringing this dark data to light, and now we are able to precisely predict why certain things are happening, this analytics now becomes very, very powerful and more accurate. So that is where big data analytics is becoming more and more powerful these days. So it is not that big data analytics can be done without getting all this. Yes, big data analytics, if you want to do it, you need to ensure that you bring the dark data to light, and then you are able to do this analytics. So this is the reason why today enterprises are looking towards big data. Any questions? So this is one aspect which we are looking at. What is big data Why big data? And this is purely from a business perspective. Now there is technology perspective, and which we covered last time in detail. The technology perspective is to say that when traditional systems are not able to handle the data, for example, this RDBMS is not able to handle this unstructured data. There might be some data which is coming very fast, which is high velocity data, or the volume of these traditional systems is itself increasing. RDBMS is not able to handle the data, and in that time you need an alternate technology. You need an alternate technology here, and this technology is known as big data, and this is the technology view of big data. So technology view is focusing here, is focusing on handling the volume, velocity, variety part of the problem, while the business perspective is focusing here at the analytics aspect of the big data. So there are two areas which you need to always remember when you enter into a big data project. Whether your project is focusing here or your project is focusing here. Now, when we started doing big data, majority of the projects have started focusing here, understanding the technology challenges and replacing it. But today, in 2014, the focus has been shifted towards here. Till 2000, late 2012, 2013, this was the focus. But now the focus is here. But the industry which has not adopted big data earlier are still focusing here. So the journey starts like this. Whenever anybody wants to focus on big data, they start with the technology perspective, and then it gradually moves to the business perspective of big data. Any questions? Does this make sense? Is it clear? Not clear?
Yes, it's clear.
Sure. Okay, so this whole thing which you need to remember from this is only two parts. Remember, whenever we talk about big data, it's about discovering this dark data and making it to life. The second thing which you need to always remember is it's all about traditional systems not able to handle the data, and we are looking at alternate technologies. The third part is where business wants to find new insights onto the data, and they are trying to look at this. So these three things, if you remember, you are good with at least the fundamentals of big data. So let me save this off. We go into the next layer. Now while I did all this high level introduction, let me go and look at it more from a technology perspective, a little bit detail into technology. And this is where we start with introducing what is Hadoop. So my goal now is to introduce what is Hadoop, and I will gradually come there. Okay, so just be patient. We'll start with the fundamentals and we'll reach to Hadoop. So let's take a typical application, a web application. So a web application starts with a front end. And the front end might be a desktop application or a web browser based application or a mobile based. Today it has moved to mobile as well. So you have, these are the three rendering options today we predominantly look at. So these are the three options which we look at. Now any application front end will actually connect to the application tier where the servers are sitting. So I'm leaving one layer out. I'm just going directly to the application layer. So this is the application layer, and the application layer is having all the business logic. Now the business logic computation is done on the data. Where is the data going to come from? Data is going to come from the DB engine. So you have the DB engine. Now DB engine is basically running all the queries on the data. So all the query plan and the query is basically execution is happening here. But where the data is stored? Data is not stored here. Data is stored in a file system. So you have a SAN or a NAS. So SAN, NAS, on which the data array is. So it's basically a storage array where the data is lying. So what is really happening is all RDBMS data is stored here. So today let's say it's in 100 GBs of data. The query execution usually go around, let's say 30 to 40 GB of data. So 30 to 40 GB has to come here. The result may be around 1 GB or maybe less than that, maybe 100 KB or something. Let's say we'll talk about 100 MB data, which goes to the business logic. And here maybe it makes it into 100 KB and that gets into the front end. Usually it is this kind of a ratio which goes in. So large volume, process it, push down as much as possible and do it. So what is happening is you are seeing that there is a large amount of data which is moving from here to here. A less number of more data moving from here to here and a further less number of data moving from here to here. But data is moving. Now this is traditional applications. They continue to exist and they will continue to exist further as well. What if you want to build an application which wants to query? So this is purely a query application because this is trying to understand the sales. So this is a large query application. Where you are trying to dice certain data. So the same problem exists. You will write an application that will run it on a database engine, pull the data and come through. Now imagine as data volume grows, this grows to, let's say, 100 terabytes. So this goes to 100 terabytes. Now the query engine is trying to pull this data. First of all, there is a large latency here. When I say large latency, it means the data has to be transferred. Because now we are talking about 30 to 40 GB data which has to come here. Now when 30 to 40 GB data has to be processed by the DB engine, the DB engine cries. And that is where we invented what is known as massively parallel database, MPP database. And these databases has been successful for quite some time. These are Teradatas, Netezza, etc. So these MPP database are able to handle this data. Nothing big deal. So they are able to handle this 30 to 40 TB of data. And they are able to process it and they are getting. The only problem with this is cost. So cost is going up very much. As this volume increases, the cost is increasing exponentially here. One big problem. Second problem is these databases has a rigid schema. In the sense, they follow relational schema. So, when they have relational schema, there is a problem, because when we are trying to bring unstructured data, this volume is growing because we are trying to bring unstructured data also. Now when you bring unstructured data, these traditional MPD databases are not able to handle that, because they are not catered for storing or handling anything other than relational data, because they are still focusing on relational schema. So there are two problems here. Cost, obviously, because they are trying to sell proprietary things there, and they are also trying to stick to the relational schema, which is not very suited for unstructured data. So we have two problems right now. Cost is going up. We need schema flexibility. Right? The third part of the problem is we are moving data. We need data local processing. We don't need to move. Data movement we need to reduce, which is causing latency. So these are the three problems. Now in MPP database, some part of latency is addressed, because in an MPP database, the data is stored locally on each of the nodes. They don't, and they pretty much have a highly optimized network as well. So there are two things which happens in an MPP database. One is optimized network, and second, they store locally on nodes. What this MPP database does is a parallel query engine which they run. So they can only support SQL. So SQL is the only query language they support. So you can only query using SQL. So from SQL, you can query into these appliances. They will run a distributed parallel query on the data and give you results. Problem is they have cost and rigid schema. Any questions still here? So this is where we are still today. Before the advent of Hadoop, this is where we are. Before Hadoop.
So these throw some light on nodes?
Nodes or
Yeah.
which one?
Nodes, yeah.
Okay, what is a node? Okay, sorry. Okay, it's good to ask those questions so that it is clear. So what is a node? A node is a physical compute element. So when I say physical compute element, it's a machine. Okay, it's a computer. So a node is nothing but equivalent to a computer, which is having a CPU. It has a CPU, memory, disk, and a network. Okay. So when you say nodes, it is basically there will be multiple of these connected together to form a network. So that we call each of them as a node. Okay. So node is nothing but a individual server. It could be a virtual VM also, or it could be a physical server. Either way it's fine. But node is equal to a computer for now. Okay.
Sure.
So when we look at a MPP architecture itself, so what MPP architecture tries to do is they creates what is known as a head node. One single machine which is called the head machine. All the query request, everything goes to this machine. So the user query is going to the head machine. Okay. So when you fire a SQL on an MPDB database, it goes like this. The SQL goes to the head machine. From the head machine, the query is distributed to all the nodes. So query goes like this. And then there will be a coordinator which coordinates, fetches the results, come back with the results. So it does data local processing. It is scalable. It is elastic. It is elastic with a very limited sense. In the sense, when I say elastic, in the sense, if you want to add another node, you need to go to Teradata and get the appliance. You have to go to Teradata and get the appliance. You cannot add your own appliance. When you go to them, they will charge a good amount. Okay, so this is how it works. The elasticity is there, but it is limited because you need to only use their appliance. Second thing is, usually these are homogeneous. In the sense, the configuration should be almost the same. So they give specialized hardware, and all this hardware configuration should be almost the same. So this is two big challenges again with scalability of these MPP databases. It does work. Nobody is saying that these are not going to work. But as the volume increases, the cost per terabyte, this is the measure of big data. Basically, we usually measure using this, increases. The cost per terabyte increases. Now, why are we storing all this data? We are storing this data to derive insights from the data. Now, if the value of that insight which we generated far exceeds the cost of storing and generating it, then it makes sense. If the value of insight is less than the cost of processing and storing, it is not worth it, correct? So that is the reason the value of the insight is becoming lesser. Why? Because the cost of processing and storing is increasing. And this is the precise reason why historically we didn't store or use the dark data. We didn't use the dark data because this equation is very, very important. If the value of the insight is not more than the cost of processing and storing, then it's not really useful to really do that processing. So for example, I take all your contracts. I did lot of processing, lot of massaging, created a big Teradata system and created a report. Now the value of that report is not really useful to substantiate the cost of storing and processing and all of those. Nobody is going to fund this. So that is the reason the data has been kept as is and the dark data exists there. So cost is a one important factor. Even though not very explicit, it's a very important factor. And in the whole economics of big data, this equation makes a very important sense. So what we are trying to do is, we want to bring the dark data to life, but keep the cost per terabyte less. Okay. So this is the another fundamental which you need to remember from big data. That is, try to keep the cost per terabyte less. If you keep this less, then only the value is there. Otherwise, there is no value in whatever you do. Make sense? Okay. So now we have understood how traditionally it has been working, how our MPP databases are been there for years. And this is where we jump into the next place, which is what is Hadoop. So let's look at what is Hadoop. What we are saying is we have large amount of data. We have large volume of data. For now, let's only focus on volume. Large volume of data. Now, I want a system where I can store this data So for example, I want to store this petabyte of data. I have 1 petabyte of data and I want to store this. Now traditionally, if I have to store this, what I will have to do it? I will have to build a massive system. So first I will spend time in building the infrastructure. Okay. It is not enough that I build the infrastructure. I need to model this data because my infrastructure only supports relational data. Now what happens if this data was having unstructured data or any other structure which doesn't fit into relational schema easily? Then what you do? You need a transformation layer here. Again, the easiest transformation layer was an ETL, like Informatica. You have data stage and so on. Pentaho, Talent, all these are ETL tools. So what you would do? Now you start a ETL project. You start a data modeling project. So you start 3 things. You first build infrastructure. This is one project. You start another project which is the data architecture project. You build schema, understanding the data and all. You start an ETL project. So build a ETL. Then you also build a data warehouse. Correct? LDB and so on. Then you hire a database engineer, and this project typically runs from, let's say, if you look at this life cycle to finally to go live, this usually takes around easily from 8 to 12 months, and that's the easiest. If the volume is petabyte, you would really struggle from here into 1 in 12 months. Now, by the time you model this data, you got this relations, you came to the reports, the business has changed. 1 year things go from this side to that side. Again, there is a new bunch of data sources which you need to integrate because the company undergone to some mergers and acquisition. So now you have fresh set of data. Again, new set of projects, new set of things before you really get into this. This cycle is what is today's data warehousing life cycle. Data warehouses and business intelligence life cycle today is like this. And this is one reason where business is frustrated, that I am not able to see any agility in this whole process. I need this to happen faster. I just cannot waste all these things. So what is the biggest thing which you need? I need flexibility in the storage. I don't need all this 1 petabyte data at the report level. I don't even know whether I really need it. I need a flexible place where I can dump this data. So the new paradigm is like this. You take this volume of data. So you take this volume of data. You dump this data into some location. Okay. And for this location, let's say this is called the dumping yard. What you do on this is you can run some few enrichment on top of this data, and that too on demand. Let's say if today you want to take few fields from one place, So you want to understand a particular weblog data. Let's say some IP address is a field in the weblog data. You want to use it and figure out which IP address are mostly coming to my sites, which geography is coming to my site. I want to analyze. So I will just do one small enrichment on that data. So this is called the enrichment. So I will enrich small part of the data, which is what I need. And then I quickly create a report out of this data. Now if I like this report and I say that okay, this report looks to be good, I want this every day, every night, every hour, I can then go ahead and build this, correct? Then I can say okay, from here to here I am going to build a process. So this is what is known as explore and productionize. So going forward, people want to go in this life cycle. Explore the data, validate the results, and then productionize. This is a whole new paradigm. And this typically the life cycle is around 2 months or 3 months max. You pretty much get here in 3 months. So the data comes in 2 months, you are here, you are able to, in fact the exploration is instantaneous. You don't even need to wait for 2-3 months. I am talking about this productionization, which is 3 months. So you get the data, you dump it, you run some queries on this data immediately, enrich, get the report, see the output. After that you decide to productionize it. So this is one big difference which is happening today from data warehouse life cycle to a big data exploration life cycle. Not everybody is following this right now, but this is one of the biggest advantage as enterprise will go into the next layer. So this is one more reason where big data is becoming more and more popular. Now why did I do all this? I wanted to explain you the concept that you don't need a rigid schema. You need a flexible schema. You need basically an on-demand schema on the data. And that's where Hadoop is going to help you. Now how Hadoop is going to help, we will see that. But this is where one of the important aspect of big data lies. That is on-demand schema. We call this as schema on read. This is the fundamental number one. Schema on read versus schema on write. In this case, when you write the data to the model, you have to define the schema. And the schema is already there and validated. Schema is validated when data is written. That means schema on write. Here there is no check. You just dump the data. Whenever we want to run a report, we apply the schema on the fly, and at the time when the query is running, the schema is validated to check whether the schema is right or not. So that means schema on read is applied. Now this becomes a very important concept because this saves a lot of time for enterprise. Rather than modeling the data upfront, keeping all the model data and all of those, we go into what is known as schema on read. You dump the data and you can apply the schema on the fly and query and get the result. Is the concept of schema on read clear? I have just explained this concept of schema on read. As I introduced to the point of what is Hadoop. I am getting to Hadoop, but before getting to Hadoop, I have just introduced one important aspect which is known as schema on read. Any questions on schema on read. Sorry? Yeah, Kavita, I think it's echoing for you. Where is it? Can you type your question? Or just remove your speaker, that would be the best. If you come on a microphone, or the other option is usually it is better to dial in into the from US. Go ahead with the question, or you can type it. Sorry. Yeah, while she writes the question and types it, anybody else has a question? So I have not really got to Hadoop yet. I'm just trying to build a base so that you understand the fundamentals on what I'm getting to. So there are two fundamentals now we have covered. One is data local processing, which we saw in the previous area. We should not move the data across the network. We should try to process the data as close to the data as possible. Second thing which we saw is what is schema on write. Okay, and Kavita has a question now. What is schema on read? How do you create a schema on demand? Okay, so
yeah. Is this better?
yeah, this is better.
Okay. So what my question is, second set of figures just in the dumping out. I think I can hear my own voice.
Oh yeah, but I am not hearing, so I think it's fine from my side. So it's
Okay. Dumping yard where you're saying we can create a schema on read or and so when we don't know the structure, totally unstructured data, right? How do we go about it? Like how do we by that? Like how exactly on there?
okay, so let me explain how this schema on read will work. Okay, and in the next two classes, once I get to Hive, you will see this in action. But today, let me just give you an example and see whether that really helps out. So this is schema on read. Here is how it works. For example, let's say you have a textual file, a large text file. In this, let's say there are fields like employee ID. Let's say pipe is the delimiter, age, gender, salary, and let's say department. So this is the file. Now this file doesn't need to be pipe delimited or anything. I am taking a simple example here so that you all understand. So this is a text file. Okay, a text file which is a delimited file with pipe as the field delimiter. Now when I dump this file into the dumping yard, I don't really tell it anything that it has these fields, this has these pipes and nothing. I just consider this as a text file, and this file is, the file name is employee.txt. So this file directly goes into my dumping yard. Okay, so just dump this file into my dumping yard. So in this case, the dumping yard could be a Hadoop environment. Now why do I need a Hadoop? I can store this into your local file system. Yes, correct. But for example, if this file is a terabyte file, 1 TB file, your hard disk might not be able to process all this. So for that is where you put it into a dumping yard like this. Now this dumping yard has many other capabilities. Right now we are just dumping it. So now I want to find out on this file, get me sum of salary for a department where age is greater than 25. Say that this is the output I want, and maybe I can say get me only for male also. That also I can do. Now this is the query which I want to analyze, or This is a simple analysis which I am running. Now I want to ask this query to this particular file. Now before I ask to this file, I can apply a schema on demand here. I can say to some system. In this case there is a system here, and to this system I will say, hey buddy, this file is going to have this kind of a structure. Okay, so to this system I will tell you on demand that this file has 5 fields and the fields are delimited by 5. So I will tell it like this, and then I will say, now you know this, all these fields and stuff like that, get me this result. What will happen is the system here will dynamically parse this file. Okay, so it will do dynamic parsing of this file. It will create this file into fields, run my logic on top of it. So execution logic, and it will give me the result. So this is what is known as schema on read. On the other hand, if I were to do it in our traditional way, when the file is loaded itself, I will have to tell, okay.
What you are explaining there, the system is typically done by the SQL loader in a mouse.
No, this is not a SQL loader. This is a Hadoop system. For now, I called it as a system. For now, let's assume this is Hive. So there's a Hive is one of the ecosystem component, okay, which is there in Hadoop, where you can define this on demand, okay, and it will automatically create this code for you on the fly. It will parse the file, get the thing, and return you the result. Okay, so this is not an RDBMS. This is just a raw file system. I am able to query a raw file directly. This is raw file. No structure change, nothing. This pipe file is just stored as is. And when I asked it to run this query, the system automatically parsed it, executed it, and gave me the result. Now the fundamental difference with RDBMS is, in an RDBMS system, if I have to do this, first I have to define the schema in RDBMS. Correct? I need to define an employee table in RDBMS. Then I have to physically transform this data into this table. Now there could be many ways to transform this data, but when the data is stored here, it is stored in rows and column format which DBMS understand. So the data is converted here already. Data is validated and converted to RDBMS format. So there are two problems which you have already gone through. You have already created the schema when the data has to be even brought in. You also converted the data to the right format. And after that only you can do this query. Now you can query on this RDBMS. I hope you see the difference. Here all this transformation, parsing, everything is happening at the load time. Okay, here is what is happening. Everything is happening here. The transformation, parsing and converting into the required structure and validating each of the fields. In this particular example, it is not happening that time. The file is just dumped, and when I want to analyze, I can. So for example, if I didn't need the salary, I wanted only, let's say, the gender, it would not even go to the salary field. It will only parse the fields which I need. And even if the salary field would have had junk in it, it will not have mattered for me. In this case, if the salary field is junk, this initial load only will not work. The file will fail. In this case, the file will go in. The salary is junk. Only when I query salary, it will get impacted. It will not get impacted otherwise. I hope this is clear.
Yes, yes, sir. That's clear. The only let's say, like, there are. So how does that kind of in that situation? Let's say there is like you.
Your sound is only coming half, so there is some problem somewhere. I think you should dial into the.
Yeah,
That is the
the
best.
first is I can hear my own voice. It's kind of like really bothering me. Yeah. What I was asking is, let's say if there is the data quality issues are there. There is anomaly in the data, and then, like you said, there is a junk salary data there. How do what happens in that case? Like, would the query fail to process, or like, when you query the Hadoop, or like, the data dump, what happens to that particular situation?
Yeah, so now when you have the junks in that particular column, yes, when you query that for that junk column, it will fail. Okay, so that is going to be, obviously it will fail for that column. Okay, but then you will know that, yeah, it is junk. Now you can transform the data, you can maybe give a default value to it, and so on. So when you in a query only, you will handle it. So it's a new paradigm of how you handle the data. Okay.
Okay.
Yeah, and I got your problem of echoing. I think I am also on speaker, so that is the reason. I will try to see. I'm trying to get.
Yeah, thank you.
Yeah. So usually I put my headphone. Today I have not put my headphones. Anyway, so we'll continue, and the next question when you ask, I will try to adjust. Okay. So till now we have only addressed 2 or 3 questions. We are trying to get into schema on read, okay, versus schema on write. We understood data local processing, which we have not got fully. So let me do data local processing one more time, a little bit more detail. But schema on read, I think, is very, very clear from these 2 examples. And thanks for asking that question. The more questions you ask, the more detail I get in. So it makes helpful for everybody else. Okay. So please keep asking the question, that will help you. I'm not worried about the time. So it's more about to get the things done is what we need to do. So schema on read. Had she not asked that question, we would not have got into this detail at least. Okay. So good. So we'll go to the next part of the problem. Okay. And this is, I'm building for Hadoop again. This time I'm going to focus on data local processing. So this is my focus area. Okay. So what is data local processing? So let's take our big file only. So our terabyte file of employee. Same example, 1 TB of file with 5 fields for employee. Now I want to run the same query on this file. Sum of salary, and this query is going to be there for you for quite some time, even with MapReduce also. So remember this query. It is select sum of salary where age greater than 25, group by department. This is the query which we want to run on this file. So what I do, I want to store this in a system. Do you think a normal system will be able to store this 1 terabyte of file? It's difficult. So let's take a typical computer. Okay. So let's say one computer, or I call it as a node for now. This node has, let's say, 16 CPU, or I could say 8 CPU, 8 into 2, 8 CPU, 2 cores. Okay, so that is makes it around 16 cores. So I hope everybody understand the principle of CPU and cores in a processor. You need to be clear with these terminologies now, because you are entering the world of scalability. So you will keep hearing the sizing in cores, CPUs, and so on. So CPU is the processing unit. It can have multiple cores. Usually it's around dual core, quad core. So quad core is 4, dual core is 2 cores. So when you multiply these two, you will get the total cores. These are basically the processing units. And let's say you have a 64 GB RAM and you have some hard disk. So let's say 250 into 250 GB into 2 to drive. I'm just keeping it less. Usually it will be in the range of 500 into 2 or 500 into 4, or it could be into 2 TB, 1 TB into 4. So in that range. I just kept it less because I don't want this 1 TB to fit into that. I kept it on purpose so that this 1 TB will not fit in. So you need 2 machines now, correct? So if this file cannot be loaded into this, you need 1 more machine. So let's say we take 2 machines and we put this whole thing into it. Again, this will be the 16 core machine, 16 cores, 64 GB and 500 GB of hard disk. Okay. So now you have a 2 system which will, now this 1 TB will fit into this. So how will you fit this data into 1 TB? First you have to break this file, correct? So you'll break it into half, let's say. You break this into half, one part of the file you will put it here, one part of the file you will put it here. Now when you want to run a query onto it, it becomes difficult, correct? How will it know which is the first part of the file, which is the second part of the file? So you really need somebody to manage this whole thing. So you need somebody like a metadata management system, which will be a separate machine. For example, let's say for now, let's say take it as an 8 core, 64 GB, and let's say 250 GB disk machine. So what it will do is it will keep a lookup. It will say file 1 is broken into part 1 and part 2, and part 1 is stored in node 1, part 2 is now stored in node 2. If it makes a metadata like this and keep it here, now anybody who wants to access this file can only go here. So the query, if he wants to access this file, it can go here and it will say, okay, node 1 is the first one, go get from the node 1, go to node 2 and get it. So this guy can understand and reconstruct the file on the fly. Now reconstruction is done, but that doesn't solve the problem. The problem is we need to scan the entire file and get the sum of salary, which means you need to run a distributed processing on both this machine. So you need to write some logic which will go after this distributed processing. But I don't want to write any distributed processing. I want to just give this processing to somebody. Let's say I give it to somebody, and this somebody can be, let's say, a compute engine. Now this compute engine will manage the distribution of the processor. Similarly, this unit is managing the distribution of data. I hope some part of it is clear. I know it is not very clear. So let me make another attempt at this diagram in a little bit different form. Okay, we'll come back to this diagram in a minute. I think I didn't start the right way. That's the reason it didn't end in properly. So compute engine, I'll just leave it here. I'll come back. Let's take a plain simple example. We have 3 machines. So forget that previous one. I'll come back to that because I didn't introduce this before I went there. So I have 3 machines. I have 16 core, 64 GB, let's say 500 GB, 500 GB of disk and 64 GB of memory. And the same thing exists here also. Let's say I have only 8 core here, 32 GB of memory and 250 GB of disk. Here I have, let's say, another 8 core, 32 GB and 250 GB hard disk. Now when you have a file which is larger than this one machine, you want a system which will give me a virtual view of, like, I have as if I have the whole disk at my disposal. So that is 1 TB, which is the addition of 500 plus 250 plus 250. I want somebody to give me a file system of this size automatically. And this file system is known as the distributed file system. So when I want to process distributed, I should be able to get a virtual view like this. For example, now if I add my one more machine to this network, I should, let's say, 8 GB, 8 core, 32 GB and 250 GB disk. If I add it, my system should automatically become 1.25 TB. So if this is possible only if I build a virtual view on top of this file system. And this is what is known as a distributed file system. Because this is individual file systems. When I merge all this file system and give a virtual view, that is known as a distributed file system. Any doubt about distributed file system? Any questions on what is a distributed file system? Similarly, I need a distributed compute engine. For example, this 16 cores, 8 core, 8 core and 8 core. So that's around 32 plus 8, 40. 40 core machine. I should have a supercomputer right now. A 40 core machine with 128 plus 32 GB of RAM. So it's around 160 GB of RAM. So a massive machine is what we want. We want to have a feeling that I have a single machine of 40 core, 160 GB, 1.5, 1.25 terabyte disk. So this is a distributed compute engine. So what a distributed system tries to do is, it tries to virtualize or aggregate all the distributed cores and gives you a single view, so that you can operate on this machine directly without worrying about going to each machine. And this is what Hadoop is providing. Why Hadoop is so popular is because of this. And this is precisely what is Hadoop. So what Hadoop is trying to commoditize distributed computing. Okay, so it's basically making it, I think there's a spelling mistake there, but fine. So it's trying to make it distributed computing so simple. For example, you can keep on adding machines to this, and this machine becomes more and more powerful. And that is what is Hadoop. So Hadoop is a distributed system which enables a distributed compute engine and a distributed file system. Now the distributed file system is known as Hadoop file system, which is HDFS, and a distributed compute engine, which is initial version, it is known as MapReduce, because that's a specific framework which we are using for processing. But beyond that, we will see that in the yarn, in the new version, it actually has become a truly distributed compute engine. Okay, so when you are looking at what is Hadoop, this is what is Hadoop. What Hadoop does is, it tries to aggregate all these machines together and tries to give you a virtual view of a distributed file system, which is known as HDFS. Also, it tries to aggregate all the compute power of those machines and gives you a distributed compute framework. So with this, any data problem now can be solved, because let's say I have 1 TB of file. Even though my individual hard disk is only 500 GB, I don't need to worry, because for me, I am having a visibility to 1.25 of disk. So I am going to just call this Hadoop distributed file system and say, buddy, store my 1 TB of file. Now this file system will manage how to split, store and all of this. Similarly, when I want to process on this 1 TB file, I don't need to split this logic and split into all these places. I just give it to a single machine, which is the distributed machine, and it will try to split and process the data. So this is what is all about Hadoop. So again, I have tried to introduce Hadoop as a distributed computing framework. Any questions on this? Any questions? Is this clear? Is it not clear? Okay, so there are little questions there. Okay. Okay, so I will answer Soma, your questions I will answer. Give me some time. Ankit, you have a question. I was not seeing those questions yet. So I have 2 questions which is left. I will answer those. But before that, I just want to make sure, what is Hadoop trying to do? It's trying to make it so you see that it's trying to build a distributed file system, a distributed compute engine on top of a set of nodes. it gives you a capability of elasticity. When I say elasticity, it is you keep on adding nodes, the power of this particular machine becomes bigger and bigger. So this is one big advantage. Second thing is it's fault tolerant. If one of the machine fails, it doesn't really mind. The system will still continue. How will it continue? Because it stores the duplicates the data and all. It will take care of it. If the processing is happening on that machine fails, it will distribute the processing somewhere else. All that is there, and we are going to see all that in more and more detail. But right now I am just trying to reflect the characteristics of this monster machine. The characteristic of this monster machine is it is elastic, it is fault tolerant, it is reliable. So once you put a file into it, you don't have to worry. It is reliable, it is safe. It will ensure that it is safe. It is reliable. Okay. It is elastic. Yeah, go ahead.
This is Kavita again. Sorry, I missed a little bit of the conversation because my phone got disconnected.
Okay.
I heard all the way until where you're showing about the distributed computing engine and as well as the file system. But
Okay.
after that, I did not get those two empty boxes there.
Okay, so these two empty boxes. Okay, fine, sorry. So what I said is taking these machines together. Okay, so we created a virtual view which is a distributed file system and a virtual view of a distributed compute engine. So basically you are trying to harness the power of all the compute as a single machine. Similarly, you are trying to get all the disk as a power of a single disk. Now you have this 1 terabyte file which you want to store it. So 1 terabyte file which you want to store it. Your hard disk size is 250 GB and all. You don't have to worry about it. You can just dump into this distributed file system because distributed file system is 1.25 terabyte. So it will take care of storing your 1 TB file automatically. You don't have to worry. It will manage the splitting of the file, distributing of the file, giving the file back and all of those it will do. So the distributed file system will take care of it. Okay. Similarly, on this file you want to run that our employee query, the SQL. You don't have to do all this management of the distributed engine and what process will happen here, what will happen here, all that fault tolerance, failure, all that you don't have to worry. You just write your stuff, logic and give it to this engine, which is a very distributed compute engine which has around 40 cores and 160 GB. It will manage how to split the data, how to split the processing, run it and give it. And all details of how it does it, we are going to cover in the next 2 sessions. How a compute engine works, how a distributed file system works internally. So we are going to see that. But for today, just assume that as you add more and more machine, the power of this logical machine improves. And that's where we say it is elastic. If one of the machine goes down, still the power is fine. Okay. It is fault tolerant because it will not lose anything. It is reliable. Once you store a file, it is reliable. It will take care of replication and all of this. So this is what are some of the characteristics of Hadoop. Okay. So what is Hadoop? It's trying to give you 2 things, a distributed file system and a distributed compute engine. Any questions? So what I try to introduce is what is Hadoop. Now I have still not introduced many concepts in it, but I still made just a rush onto it to give you this principle, so that you understand what are we talking about this dumping ground. This dumping ground is this now. Now take this back to your original problem. So let's go back to the original problem now. So this is Hadoop. So let's go back to our schema and read this problem. Okay, so when we are talking about this dumping count, we are dumping this file in and this compute engine is going to actually do this process. Okay, We go further down. I think there was compute engine. So this is where we were talking about how a distributed file processing is going to happen. A file is distributed in all the nodes. When you fire a query, the compute engine comes into play and it will distribute the process. And this is our distributed file system management system. So logically you can say that this is our distributed file system, which is trying to, on this distributed file system you are trying to store the file. On this compute engine you are running all your logic. So Hadoop gives you only two parts, a compute engine and a file system. Okay. So when somebody asks you what is Hadoop, the answer is Hadoop has two parts. It has a distributed file system called HDFS. Okay. And it supports a distributed compute engine, and the framework which it uses is a MapReduce. So Hadoop consists of two parts, MapReduce and HDFS. And MapReduce is nothing but a compute framework. Now as you go further you will realize that MapReduce has some limitation, and hence you need a generic compute framework, and that's what we are heading towards right now. Okay. So when Hadoop was originally designed, this is how it was, HDFS and MapReduce, and this is what was called Hadoop. Okay. And on top of it there are many other components which exist, which are called the Hadoop ecosystem component. For example, Hive, which is a query engine, Pig, which is a data flow engine, and so on. So these are all ecosystem components. So I'm just trying to get the terminology right. Hadoop is this, HDFS and MapReduce. Anything beyond that is called Hadoop ecosystem components. And Hadoop is HDFS and MapReduce. Clear? Again, this is more for concepts so that you understand what is Hadoop. Clear? Any questions still here? So that there are many people.
Can I call Hadoop as the application, sir?
Hadoop as an application? No. Hadoop is a platform. Okay. I would call Hadoop as a platform rather than an application, because you write application on top of Hadoop. See, this logic is written on top of Hadoop. So Hadoop doesn't give you this logic. So application usually has that logic, correct? Hadoop only gives you the platform. It gives you a distributed compute engine. It gives you a distributed file system. So you should always call Hadoop as a platform, because on a platform you write your applications. Make sense?
Yes, sir.
So it's good to get these terminologies right, because when you start going in interviews and talk about this, make sure that you use the right terminologies, because with the terminology only you will know whether the person knows Hadoop or not. So when we talk about Hadoop ecosystem component, make sure that you are talking about Hive, Pig and other things. When you talk about Hadoop, it's HDFS and MapReduce. Clearly make it very terminology clear. Hadoop is a platform. Now let's look at data local processing. I actually started to explain data local processing, but I didn't really reach there. So sorry for that, but we will get there now. Okay. Because I think I didn't introduce the right way.
One other question before you proceed. So you said Hadoop is a platform, right? But that has to be installed on somewhere, right? It has to be installed, right? Like what is the requirement there? What should be the requirement to install the Hadoop?
Yeah, so what we saw is here. What we need is a node to install Hadoop. Okay. And if you look at Hadoop, Hadoop is written in Java. So you need a JVM installed on the machine. So all your requirement, the fundamental requirement for installation of Hadoop is you should have a machine. Okay, you should have a machine. Now it could be your laptop. Nobody stops you from doing that. You need to have a JVM, and if the normal version of Hadoop you use, you need a Unix machine, Linux. Okay, there is a Microsoft version, but then you have to get that clear Microsoft version separately. The reason being is, ideally when you say Java, it should be able to run it everywhere, which is fine. But there is some native components which are compiled for Unix, and similarly that has to be recompiled for Microsoft. So that is the reason this is the requirement. You need an OS which is Linux. You need a JVM, and obviously if you have a Linux and a JVM, then you will be already on a machine. So this is your requirement. Now again, if you say give me some more specific requirement, I can say that okay, give me a minimum of a 4 GB machine, or I'd say 2 GB is also good enough. 3 GB also it will work. A 3 GB 2 core machine is good enough to show you Hadoop, but it's not how you will do it in production. 4 GB 2 core is better to have it for your development and for your practice purpose. You can have this machine, you are good. Okay, so anybody who has a 8 GB laptop and all, you are have it. So you can have Hadoop in your laptop.
So that means when I install Hadoop, both HDFS and MapReduce will be installed, right?
Yeah, it will be installed. We will do it, don't worry. In the third session, we will install. Okay, and the fourth session you will install, not me. So you will install on Hadoop. So don't worry, it is all very near. It's not too far. Maybe the next week you are installing Hadoop yourself.
Okay. So, but is there a difference between installing on a Microsoft versus Linux?
Little bit is there. Okay, so Microsoft is simple to install. It's one click, but the troubleshooting is painful. Linux, a little bit more structured installation. Troubleshooting is simple, very simple. Okay, so I would prefer when you start learning Hadoop, please don't try on Microsoft to start with. Unless you are a great fan of Microsoft and you want to only stick to Microsoft, I'm fine with it. But if you are really not there yet on Microsoft, try to start with Linux, because that's a much better way to start with. And once you understand all the nitty-gritties of Hadoop, you can install anywhere. Whether you put it on Mac or Microsoft, it doesn't matter after that. So,
what about test data?
Okay, so I saw the question about test data. So you don't really need a test data to install Hadoop actually. Okay, once the platform is ready, now you want to put a file in, then you can take any of your file and put it. For example, I write a text file. Okay, I take a license file of any software and put it into Hadoop. You don't need a test data the way you think about test data. You can put any data into it. It will work. Now we will show you that also, how the Hadoop thing works. So just keep your curiosity about how this whole thing is going to work for a day or two. After that it will be all clear. Okay. So the first 2 sessions is going to be building the fundamentals. I can go to the environment right now and show you many things, but that's not going to help you anywhere. So I am trying to build the fundamentals. So first 2 sessions we are going to build the fundamentals. After that, we are going to get into the details where you will install and you will configure, you will have your environment, and then you will have access to my environment as well. Okay. Before we go there, there are 2 questions which are on the screen and I want to answer those. So Ankit had a question. My developers are saying that it's taking a lot of time to change the schema in Hadoop. Then they are actually fooling me. So you can actually do it yourself. If they are telling you that it takes a long time to change a schema, unless they have miserably screwed it up, it should not take that much time. Okay. The only way they would have screwed up is they have written the schema in a Java program and written a MapReduce on top of it without externalizing the schema. So if they have not followed all that best practices, obviously the schema is deep rooted in the code and hence you have a trouble. But otherwise, in all my projects, if today you want me to change something, I'll change it right on the live in production without worrying about anything. And there are ways to do that. So as we go through, we'll look at that. I hope, Ankit, that helps you answer that question. And I will show you in the couple of sessions. Give me 2 more sessions. I'll show you that how easy it is to do that. Soma, you had a question about the broken files records. I will cover that in MapReduce. I will not cover now. Sorry for that, because that will be too much for the guys who are just getting into Hadoop. Okay. So your problem we will address, but we'll address on the MapReduce session. The broken file record problem. Okay. Okay, so there is a question, how much of Java is really required for a developer job? Now there are multiple types of developers. Okay. So there are multiple types of developer. If you are trying to run everything in MapReduce, then you need everything to be written in Java or Python or some language. Okay. So it is not like Java is mandatory. You can write in any language. If you write in Java, it is more efficient. So people prefer to write in Java. But in majority of the projects which I worked on, and the trend which I see in the industry, I've pretty much worked on so many projects. It's not 1 or 2 projects which I'm working on. So don't think that it is just small projects which I work on. I worked on a lot of different variety of projects, different stuff. And in that projects, if you see it, Java is, let's say, maybe 5% of it. I've not really seen all my programs in Java. And the projects which I did fully in Java, that project has been literally screwed. Okay. So don't worry about Java. There are a lot of ways to do it with minimal Java, and that's the best way to do it. If your project has to have a longer longevity, it is usually projects which has very less of Java. It's only 1 or 2 algorithms which you write, or maybe 5-6 algorithms, but the rest you use the Hadoop ecosystem components like Hive and Pig and do it. Because if you totally rely everything to be written on Java, because some architects in your company actually force you to do that, you are inviting trouble. Okay. So, because go back to the principle, it's all about faster insights. Anything you write in Java will take a longer time to get written there. A query can be written in 5 minutes. So it's much better to go after queries. Now, Sushma had a question. From a Hadoop QA perspective, what is the amount of knowledge required in Hadoop? Yeah, so from a QA perspective, you need to know a great deal of Hadoop, because whatever we cover from an admin perspective is something which you definitely need. You don't need advanced developer aspect of it, but at least the admin part of whatever we are going to cover, you will need it. Because in the admin part, I will teach you everything on the ecosystem. So you will need at least till there. And if you do developer, yeah, you can be good enough. But admin is something you absolutely need to have, because you will know all the components, how to work, what it does, how to really understand the basics of each of the components. So that will be there, and you will know how to install, configure your Hadoop, how to create your test data and run it. So I hope that answers your question, Sushma. But it needs to be, yeah, all the tools needs to be known. Hive, Pig, Uzi, all tools in the ecosystem you should know as a QA. If you don't know it, it will not work. So you need to know all the tools, and that's the thing which we will cover. Okay. You cannot just say that I know only HDFS and I know query, I will be able to do QA. No, you will not be an effective QA at all, because you don't know where the problem is and how the problem is going to come. So your test cases are not catering to any of this. So I hope I answered Kumar's question on Java developer. Okay. So there are multiple types of developer. So one is a pure Java developer, and that people will expect that he is a Java expert. But there are other developers which are used for Hadoop, and they are pretty much ETL guys. Anybody who knows ETLs, or those guys are able to do Hadoop projects. Okay. I hope that answers all the questions which I have on the screen right now, and I'm going to move forward to few more things before I stop for the day. So one small problem, the problem being my screen has hung. So just give me 1 second. I'll be back in a minute. I'll be back in a minute. Just give me 1 second. Still some problem. Okay, I think I'm back. Okay, so there is a slight problem. I think anything further will not get recorded properly. Soma, can you do me a favor? Can you record it for today? Soma, you're there? Soma, I have just made you the organizer. Can you just record for me? Just give me 1 more second. I just want confirmation from Soma that the recording is happening. So,
Yes, yes, can you hear me?
yeah, I can hear you now. You started, or you're you're not able to get the start the recording button?
Oh yeah, I have it. I'm doing it now.
Okay, just let me know once it is started, because otherwise it will not record. It will only record voice.
Yeah.
Okay, fine. Thanks. So we'll continue.
Yeah, no problem.
Okay, so we'll go ahead and do the data local processing. So one thing which we need to know is we were having multiple machines. Now we said that when we tried in a DBMS engine, data was moving across the network. We want to stop that. We want data to be split. So let's say it was a terabyte of file. So this was a terabyte file. What we expect is this file should be broken into pieces and stored into these machines. So let's say for now I broke it into 4 parts. So this is part 1, part 2, part 3 and part 4. Now I can do it in 2 parts and 1 part, or 4 parts, or 20 parts, or different. Now let's understand why and how much part should it be broken. For example, let's take 4 parts. If I break this file into 4 parts and store it in these machines. So let's say I store it in Here this is part 1. I stored part 2 here in this machine. I stored part 3 here. And I stored part 4 here. Okay. So when I say I want data local processing, I need this part of the file to be processed in this machine. This machine has a CPU right now. Already we said that this machine has 16 core CPU, 64 GB RAM, and it had around 500 GB disk. Out of this, since it's broken into 4 parts, this will be around 250. So 250 GB. We have 250 GB here. And so these are 2 parts of 250 which is stored here. Correct? Now when I want to run some processing, I don't want to pull this 250 GB out. I would expect that the processing will happen here locally on this machine, so that there is no data movement. Why should I not do data movement? Because data movement will cause latency. So you use data local processing to avoid latency. So this is one more big principle of Hadoop, that you try to process where the data is residing rather than move the data across the cluster. So when we store the data, we split it and store in multiple nodes on the cluster. Okay? And then we push the code towards the data. So we move the code towards the data. Move code towards the data and not data towards the code. In traditional system, we move data towards the code. Now if the data is bigger, this becomes a bigger bottleneck. While code is usually of the order of, let's say, 100 MBs or maybe 1 MB. So we usually have less code to move. So data local processing involves moving code towards the data. Remember that. So big data, this is one of the biggest principle, that you always move code towards the data. Now this is one principle which we already understood. So that we broke the file and then we send the code down to each machine. Now let's look at the second part of the problem. Should I break it into 2 parts or should I break it into 4 parts? The beauty is that the more the parts, the more parallelism it is. Are you getting that? More parts of the file, more parallel execution. So you will get more throughput. So you should ideally not split into 4, correct? You should be splitting into much more smaller pieces, because the more smaller pieces you create, the more parallel code you can execute. Now if you make it very small, then it becomes a problem. So you should not make too small than the number of cores we have. So if you have 16 cores, 16 parallel executions can happen, correct? So if you go more than that, execution will not be parallel. So there is definitely a relationship between the number of cores and the number of parallel process which you can run on the machine. Is that clear? So parallelism is controlled by the number of cores. If you don't split enough, then even though the core is there, it will not be able to use it. So you need to ensure that the files are also split into smaller pieces. Okay, the file is split into smaller pieces. Why it is split into smaller pieces? Because more smaller pieces, more parallel can execute. But this parallel reaches a saturation. When it will reach saturation? When the number of cores on that machine gets exhausted. So there is a trade-off. The trade-off is how much splits can you do and how much cores exist on the machine. Is this point clear? So there is
I have
one
a question,
more.
Satish here.
Yeah, go ahead, Sashi.
See, when we split the data into small pieces, obviously it's like we are increasing the load, right? When we access parallelly the data,
Yeah.
that's how it works in normal traditional databases.
Correct. So you are trying to increase the load because you are trying to increase the parallel thing, correct?
Yes,
Now
exactly.
you are trying to use the machines more effectively. For example, if you have 16 core machine and your utilization is only 20%, okay? If you are utilizing this machine 20%, that means 80% of 16 core is idle, doing nothing.
Yes.
Okay? So that is not what you need to do. You need to try to maximize it. Now again, you should not be doing 100% utilization. Because if you do 100% utilization, that means somebody is starving. Correct? So you should come to some optimized utilization, maybe 85% utilization on the machine. So you should not have 20% utilization, but you should have around 85% utilization. So you should design your system, and when we look at capacity planning and sizing of Hadoop, we will see how you should design the cluster such that you reaches only this kind of numbers and you have an optimized parallelism which is done. So there are multiple factors which needs to be considered. The file is the smaller file, the cores on this machine, the utilization of this, the kind of workloads, the data which gets transferred across the network, and so many parameters. Okay, so don't worry, we will cover those. It is all coming up as part of our capacity sizing. For now, I am just trying to introduce the concept. The concept being is we need to ensure that these files are split into smaller size enough so that there is enough splits available for the computer to run. That is one. At the same time, you should not exhaust all the cores out here because the parallelism is controlled based on that. Okay, so these are two things which I can't do. Apart from that, how to decide the block size and all, we are going to come there. Okay, so Ankit had a question. What is clusters? Correct? So the question is clusters equal to nodes? No. Clusters is not node. Cluster is group of node. Okay. Cluster is a group of node. So this group of node becomes a cluster. Okay. So cluster is a group of node. Okay. I hope that answers that cluster question. I also try to start with saying that we did data local processing. We should not move the data. We should split the file in smaller pieces so that you have more parallelism. Should not split more so much that your cores are getting overloaded. Okay. You should design the system optimally. We'll come to that design part of it. Now let's look at it. One more concept which is called block storage concept. Block storage. Okay. We'll look at that soon. Before that, there is a question from Panadi. If 100 nodes are there, do we still call one cluster? Okay, so that's an interesting question now. It has thrown a little interesting twist onto it, saying what is a cluster? Okay, so let's define what is a cluster. I thought I answered it a little vaguely. So we'll come back there. So let me just save this file. So this was data local processing and speeds. Okay, so let's understand what is a cluster. So a cluster is nothing but a group of related nodes. Okay, so you could have tens of machines in a cluster. Okay, but they have to be related. For example, if you have 100 nodes, you can divide into 2 clusters. Nobody is preventing you from doing that by grouping them logically under one group. So you can have a Hadoop cluster 1 here and a Hadoop cluster 2 here. Okay. So logically grouped clusters, logically grouped nodes form a cluster. I hope that makes it more precise. Logically grouped nodes is equal to cluster. I hope that makes sense. Rantati, I hope that is answer. So what is the difference between a data center? Okay, cluster and a data center. Okay, so now
Logically grouping nodes.
okay, so there are many reasons why you need logically grouping, so that there is isolation. One of the biggest reason is isolation. Okay, because in a Hadoop cluster, if these all nodes are connected, the data is now shared between these nodes. So if you put test data into this, okay, so let's say you put this cluster with test data. Now if you don't put the isolation and this is production cluster, your data will all mix. Okay, so you should not do that. You should have isolation. So logical grouping of nodes are done for isolation. Now what is a data center? So there is a question like what is a data center? Okay, so there are different items when you call what is a data center. So you need to understand physically, and sometimes it is better to visit a data center. Data center is a physical location. Okay, so when I call a data center, it is a physical location where the data, where the servers are stored. Servers are stored. For example, I have my building number 1. Okay, in building number 1, I store physical servers. So I call data center 1 is building number 1. So it is called DC1. I can have a data center on building 2 also. So in building 2, physically, I put another server group and I call it as data center 2. Now within a data center, you have what is known as racks. Okay. So you buy multiple racks, and in racks you actually store your servers. Okay, so these are physical racks. Now each rack will have a network. So inter-network within the rack is all within it. Done through the internal switch there it is. Sorry?
Please over here. It says the connection with the go-to-meeting server has been lost.
Just wait for a second, it will come.
Okay.
It will come back. Okay. So this is the data center, and within the data center you have racks, and within each racks you have the servers. Server 1, server 2 and so on. And each of them are connected through a switch, internal switch. Between the rack there is a uplink switch which is there and so on. So we'll look at this physical topology when we actually try to get the topology designed done. So for now, only what is a data center? Physical location is a data center. Data center has racks. Racks has servers. Servers can have one or multiple nodes. Okay, depending upon whether it's virtualized or not virtualized. I hope that concept is clear. Okay. So I think this is too much for you for today. If I go further and further, it will not really help. So let me just summarize what all we did. We try to understand big data a little bit more today. We looked at how traditional business intelligence evolved and gone into BI system. We looked at the difference between business view and the IT view of it. We didn't look at any of this today. We didn't even look at this. Yeah, we looked at the business view, technology view of the data. Use cases we didn't do. We'll cover that separately. We looked at what is Hadoop. What is a distributed file system? We looked at it. Again, we'll look at more detail of it. MapReduce we didn't even look. We are focusing more today on terminologies. We didn't even look at any of this. But we looked at schema on RAID in detail. Data local processing. We also said network traffic we should avoid. We looked at these two, but these two we'll cover again. We'll not rely on it. So this is what we have covered till now. Okay. Any questions? So we'll stop it here for today and we'll continue tomorrow same time, because there is too much to cover. It is not worth doing all this together. We'll do it gradually. I hope you guys understand it, and I'll send you guys the pictures so that you will be able to understand and correlate, and the videos will be uploaded. Okay.
Sir, one question before we hang up.
Yeah, go ahead.
You mentioned about Hadoop ecosystem, right? You also will be covering about those topics?
Yeah. So what we are going to cover, I think I had discussed last time. Anyway, let me just show you what we are going to cover. Just give me 1 second. Let me pull the session detail plan. So this is what we are going to cover. Okay. So today we just started the introduction. There are a lot more things to go on the introduction. Okay. Then we get into the fundamentals of Hadoop. So here we are going to get into details of Hadoop, HDFS fundamentals. There's a lot more to go here. Then comes MapReduce. Then go to Yarn. Then start with installation, configuration, and so on. Okay. So we will go that. Then we look at the internals of the HDFS file system. After that, we go to the Hadoop ecosystem. We understand what is the role of each, how does it fit together, and then we just skim through it on a high level from a Hive, Pig, Oozie, Flume, Hue, Zookeeper, Scoop. These are all the ecosystem components which we intend to cover. Once that is done, then we'll go back to the administration topics and get into detail. It includes sizing and getting the high availability for recovery, backup, all that part which we will cover. We'll go into the monitoring of, again from an admin perspective. Then we go to the Hadoop schedulers. We look at what are the schedulers. This is where the capacity planning, sizing, network topology design we will cover. These are all mostly from an admin perspective. We look at from a maintenance, what should be done. From here we start with the developer part of it. We get into the details of the developer. Then we go into the MapReduce API in detail, every aspect of the MapReduce. Then we take each ecosystem component and go into the advanced aspect of it. In between we'll cover MapReduce design patterns. We look at the security of the cluster. We look at all common failures which you find in. Goes to advanced Hive. We look at Impala. Then we go to Pig. We look at advanced Uzi. Go to Hue. Advanced Flume. Go to advanced Zookeeper. Yarn. And then we end with a POC. So this is the overall schedule. It covers all developer architecture, architect and developer and admin. Now depending upon what you join to, you can join either for a developer or an admin. The usually ask for the whole thing. There is no specific architect separately. So you take the whole thing, you become an architect. You take only administration, you will drop off in the middle. You continue as developer, you go further up, and an architect goes to it. So that's the course. It need not be that you have an architect to complete the whole thing, but once you complete this whole thing, you are anything in Hadoop. So that's the goal. Okay. So I hope the course detail is outlined properly.
Yeah, yeah. One question though, sir. Let's say I have a company and then I have to kind of like, I think my voice is echoing again.
Okay, 1 second. Let me.
Okay. Let's say I have a company and I want to kind of like, start a Hadoop project. What are all the key resources that I might have to hire, and what would be the roles and responsibilities? How big is the team size, and what would be the individual responsibility? Let's say I'm thinking based on what you kind of described about the scope. There might be an architect, there is a developer, there is an admin. Apart from that, is there going to be a requirements person, or how does the whole project look like? Hello? 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 Hello, can anyone hear me?
Yeah, I can hear you.
Hello? Oh, yeah, I can hear you. No, I can hear.
It seems like Sudesh got muted.
Yeah.
I muted myself. Okay, okay.